Those of you attending our webinar live today, thank you for joining us. This is the 8th NGL webinar. And today I'm delighted to welcome my PhD co-advisor and our NGL webinar speaker, Russell Green. He's a professor in the Department of Civil and Environmental Engineering at Virginia Tech in Blacksburg, Virginia. And he's made many significant contributions to our field of earthquake engineering, including studies in paleoliquefaction, seismic hazard analyses, numerical site response analyses, liquefaction evaluation, and in situ characterization of soil properties. We're very eager to hear his insights on a key topic that's relevant to our ongoing NGL model development activities. So without further ado, I will turn it over to Russell.
Thank you, Kristen. And thank you to the organizers for inviting me to present. For those that attended the Geo Congress, you're going to recognize probably about 80+% of this presentation. But I know a lot of people weren't able to Geo Congress, so it may be new to many of you. The title, I worked on the presentation since I was invited and modified the title several times. So the final one now is the regionalization of the simplified model and separating liquefaction, triggering, and manifestation. And the integration of those two will become apparent in the presentation. For the acknowledgements, this work has been going on for 10+ years, and this has been in collaboration with a lot of students and colleagues, both from Virginia Tech and other institutions. And here's a list of the ones that I could think of when I was putting this together, and I apologize if I missed anybody. But I particularly put the students that have worked on various aspects of this in bold because this really was their work. And then also for the funding agencies, it came from a range of places: NSF, USGS, GEAR, NAM, Virginia Tech, the University of Canterbury, and the University of Auckland. And I'm sure there was other funding involved. And again, I apologize if I left anybody off on that. But for an outline of the presentation, I'll give a short background on the liquefaction triggering and the simplified model. The reason for this is because when we start talking about the regionalization of the model, I want to make sure that everybody understands what I'm referring to. And so the background may or may not be needed depending on your background on the simplified procedure. Then move into the regionalization of the simplified model, manifestation severity index models, and then the true liquefaction triggering curve. True doesn't mean it's correct. Hopefully it'll become apparent as I go through. It means that it's separating triggering from manifestation. And then just a brief summary. All right, so starting out with the background of the simplified procedure. This is the most commonly used approach for evaluating liquefaction triggering. The word simplified was originally used because you didn't need to use numerical site response analysis to compute the seismic demand. It used a simplified form of this, but now the simplified procedure kind of encompasses all aspects of the model. This was developed independently by Professor Whitman out of MIT, and then also Professors Seed and Idris out of UC Berkeley. And it's a semi-empirical approach. Unfortunately, a lot of the underlying mechanics of the approach are kind of overlooked or kind of obscured by the empirical aspects. And this manifests in a few different ways to include the separation of the triggering and manifestation. I had mentioned that Seed and Idris and then also Whitman independently developed a simplified procedure. I went back to their respective papers. On the left, you're seeing the simplified curves from the Whitman. You can see on the vertical axis, he has cyclic stress divided by the initial vertical effective stress. So this is what we now refer to as the cyclic stress ratio. And on the horizontal axis, he uses apparent relative density, which he estimated by normalized penetration resistance. And he had a total of 13 different cases plus some laboratory data to develop these curves that you're seeing here. And then off to the right is the curves proposed by Seed and Idris. The Seed and Idris paper was largely, or had a large component of laboratory testing, where the original Whitman procedure in 1971 was really based just solely on field testing. But the Seed and Idris procedure, you see maximum ground acceleration on the vertical axis and then relative density on the horizontal axis. And they had a larger case history database where Whitman had 13, Seed and Idris had 35 cases they used to derive their curves. All right, so back to the definition of simplified. As opposed to performing numerical site response analyses, the estimated cyclic shear stress at depth in a profile was determined using Newton's second law, and that is F equals ma. And what they assumed is you had a rigid soil column, you knew what the peak ground acceleration was at the ground surface, and what you were interested in doing is computing the shear stress or the maximum shear stress at some depth z. And again, starting with Newton's second law, you can go through a series of substitutions and you end up with this, the shear stress or the maximum shear stress at the base of this rigid column is going to be equal to the total stress divided by the acceleration due to gravity times the peak ground horizontal ground acceleration at the ground surface. So the rigid soil column doesn't represent what we have in the field. So there needed to be a series of corrections and normalizations, and many of these evolved over time. And the resulting curve or the resulting equation that we use for our normalized cyclic stress ratio, which I'm designating as CSR star, is 0.65 A max divided by G, your total stress divided by your initial vertical stress, R sub D times 1 over magnitude scaling factor times K sigma times K alpha. And if we go through specifically what these normalizations are, you can see that you have the components that were for the rigid soil profile highlighted in red or bound in red. Then the normalization for the fact that we don't have a rigid soil profile, but we have a non-rigid profile introduced R sub D. We're doing this for a reference condition for a magnitude shaking for a magnitude 7.5 event. And that includes two components, the 0.65 and the magnitude scaling factor. And you could argue that the 0.65 really doesn't deal with the duration, it deals with the amplitude, but inherently they're linked, and I'm going to go ahead and lump those together and say both were used to represent duration. Then we have the dividing by the initial vertical effective stress and the introduction of K sigma to get it to 1 atmosphere overburden stress. And then finally, no static shear stress or level ground conditions, the introduction of K alpha. So all of these conditions that I'm showing in the bullets are representing what our reference conditions are. And the way this is used is you compute the cyclic stress ratio for sites that were impacted by an earthquake. For sites that had observations of liquefaction, you use 1 point to designate those. You characterize the site using some sort of in situ test. In this, I'm showing that they're using normalized cone penetration resistance. You do the same thing for sites that are liquefiable, but showed no evidence of liquefaction, and just designating those with different points. And you can see that these two groups of data kind of fall in different regions on the plot. And what we can do is separate those regions with a curve, and that's referred to as our cyclic resistance ratio. And this cyclic resistance ratio curve, or normalized cyclic resistance ratio curve, corresponds to the reference conditions that we went ahead and normalized our cyclic stress ratio to. And the way we use this in a forward analysis, we compute the factor safety against liquefaction with the traditional definition of factor safety being capacity divided by demand, which means for the liquefaction, it's going to be the CRR star divided by CSR star. And our CRR star is going to be determined by performing in situ tests at the site of interest. Our CSR star is going to be determined from our design earthquake. And inherently, liquefaction triggering is a low cycle fatigue phenomena, which means we have to have an amplitude and durational components. And if we look at the CSR star, you can see how I broke this down into the amplitude component and then also the duration component. And again, everything is being normalized to those reference conditions. And in addition to saying it's reference to the shaking duration of a magnitude 7.5 event, because I'm going to talk about the regionalization, it's actually the normalization to a 7.5 event in an active shallow crustal tectonic regime. And the reason for that is the durations characteristics can actually differ in different regions. So magnitude isn't all encompassing in capturing or characterizing duration. And building on that, if you look at our demand expression, our CSR star, there's two particular relationships within this equation that are actually regionally dependent, and that's the R sub D and the magnitude scaling factor. And going back to what those are, R sub D accounts for the non-rigid response of the soil profile. There's many publications, and they typically are often referred to it as it relates to the nonlinear response of the profile. That's true, but it's more correct to say non-rigid response. If we had a linear elastic profile, we would still need an R sub D. And so now if you have a nonlinear profile, you're certainly going to need an R sub D. So I think the most correct way of stating what R sub D does is it accounts for the non-rigid response of the profile. And then the magnitude scaling factors accounts for the duration of the shaking and the motions in terms of number of equivalent cycles. And this is relative to a magnitude 7.5 event, and again, in an active shallow crustal tectonic regime. So now looking at these parameters, R sub D and magnitude scaling factors, and how we develop those regionally, what we do is take soil profile and also ground motions, and we select these for being representative of whatever region we're interested in. And I'm doing these regions fairly crudely: Western US, Central Eastern US, Pacific Northwest for subduction zones, and then even within these different tectonic regimes, whether we're dealing with natural or induced seismicity. And once we have our representative profiles and ground motions, perform a series of site response analyses, and then we're able to get relationships for number of equivalent cycles, and then also R sub D. And these relationships are going to be region specific, and then they're also going to be correlated if you're doing a probabilistic type analysis. So we'll have a distribution around each of these, but if you pick a low value here, it might mean you have to pick a high value here because they are correlated. So back to what R sub D and magnitude scaling factor represent. When we're dealing with a regional, it's going to be a function of the properties of the soil profile. So our profile stratigraphy is going to be a function of our shear wave velocity and impedance contrast. And the predictive parameters that we've commonly used are going to be VS12, or our average shear wave velocity in the upper 12 meters of the profile. This was originally proposed by Chetton, and we've done subsequent analyses, and it actually works well in most of the regions we've looked at. And then also there's going to be a regional dependencies. Also have the stress strain response of the individual strata. I'm not sure if that's regional. Probably if geomorphology would be more of a proper way of saying that it's dependent, but potentially regionally dependent on a broader scale. Also depth of bedrock and the bedrock stiffness. And then the characteristics of the ground motions, it's going to be the amplitude of the ground motions, which we typically represent by A max, which is our peak ground acceleration in the horizontal direction at the ground surface. Our frequency content, which we typically represent in terms of magnitude, but also a regional. And then duration with peak ground acceleration, magnitude, and regional. And I'll specifically point out this peak ground acceleration because this hasn't traditionally been included as far as a duration predictive measure. So looking at updated R sub D relationships for the Western US, and the Western US is going to be our reference condition. When I refer to the Western US, I'm referring to an active shallow crustal tectonic regime. So I have two plots. One on the left is the depth on the vertical axis and R sub D on the horizontal axis, and this corresponds to a magnitude 5.5, and I'm showing 4 different curves. The 3 of the curves that fall to the right are actually ones that have been previously used, and the one that we developed is the one that falls to most to the left. And then similar plot, only now for a magnitude 7.5, you can see that these curves kind of bunch together a little bit closer. And so you can see for lower magnitudes is where we would get a bigger discrepancy using existing R sub D relationships versus the newly proposed one. Number of equivalent cycles, we're using this to represent the duration. We performed a series of numerical site response analyses, computed the duration for the different ground motions at different depths, and then looked at different predictive measures or parameters to use to quantify this number of equivalent cycles. And we ended up finding out that it's related to A max, or the peak ground acceleration at the ground surface, and then also the magnitude. And the introduction to the A max, I actually resisted for a while, and then in retrospect, I shouldn't have. And the reason is if you think of near field motions, and particularly if we consider directivity. So if we have a given magnitude event and we have a given site to source distance, and let's define site to source distance as distance to the fault. If we have forward directivity, typically we have a larger amplitude and a shorter duration. And that's for a given magnitude event and a given site to source distance. If we have reverse directivity for the same magnitude and site to source distance, what we have is a lower amplitude, but a longer duration. And even though that the forward and reverse directivity may be the extremes, we end up finding out that this holds all over the entire area impacted by the shaking. And as a result, the inclusion of Amax actually gives us a much better correlation with number of equivalent cycles than just using magnitude. And the way that we relate this to magnitude scaling factor is we have number of equivalent cycles for our reference condition, and that's going to be a 7.5 event in the Western US. And then the denominator is going to be number of equivalent cycles for a given magnitude, and that could be regionally dependent. And this is raised to a power of B. The B value is typically taken from laboratory tests. What we do is we plot the stress ratio on a log scale versus number of cycles to liquefaction. This often plots as a straight line, and B is the negative slope of that line. But in looking at that, we ended up finding out, and this was Kristen's work, part of Kristen's work, we ended up finding out that that B value can actually vary depending on how you define liquefaction. For loose samples, we typically use an excess pore water pressure ratio of 1. For denser samples, that doesn't hold, and so we end up using some sort of strain criteria. Depending on what strain criteria you use can actually influence the B value, particularly when you're dealing with a low number of cycles to liquefy. We end up finding out a better way of doing this is plotting cyclic stress ratio versus number of cycles to liquefaction, but doing a contour of constant dissipated energy. And it actually is consistent because the way that we compute number of equivalent cycles is using a fatigue theory, and that's actually based on dissipated energy, whether it's kind of embedded in it or kind of upfront, depending on how you implement it. And so using a contour of constant dissipated energy, we end up finding out that this B value is fairly constant at around 0.28. And another thing is that it allows you to actually be able to determine this contour and the slope for magnitude reduction or modulus reduction curves that are typically used in equivalent linear site response analyses. And the benefit of that is often those modulus reduction curves are based on a large statistical analysis of a large database of different types of soils. So now going into the magnitude scaling factor, what we end up finding out is that for a magnitude 7.5 event, that's only one of our predictive variables. We also have to have a reference condition for Amax. So what I did is I looked at the case history databases for the cases, liquefaction and no liquefaction cases that range between a magnitude 7.4 and a 7.6 event, and averaged out the PGA, and ended up finding out that coming up with a PGA of 0.35 G. So now our reference condition for that CRR curve is going to be a magnitude 7.5 event with a PGA of 0.35 G. And this is in an active shallow crustal tectonic regime. And then our denominator in this relationship is going to be a regionally dependent relationship, depending on where your case histories are, what region your case histories are from. So now plotting up our magnitude scaling factor, I'm showing magnitude scaling factor on a vertical axis, magnitude on a horizontal axis. The magnitude scaling factor equals 1 for our reference condition. That's going to be for a 7.5 event and a peak ground acceleration of 0.35 G. Any other variable, it's going to now move. So you see that not only does it have a slope, which is showing its dependency on magnitude, but it's also going to move vertically depending on PGA. If we want to compare how our predicted factor of safety of liquefaction is using the Western US or our reference condition, potentially in another area, say the Central Eastern US, what we can do is look at the factor of safety of the liquefaction ratio. So that's the factor of safety of liquefaction. And here as an example, I'm showing it for the Central Eastern US divided by the factor of safety against liquefaction predicted using our reference condition, which I'm listing as Western US. And you end up seeing that this ratio is going to be the ratio of the R sub Ds times the ratios of the magnitude scaling factors. And so this now allows us to determine whether we're conservative or unconservative using our standard triggering procedure in different regions. And first, we'll look at the central and eastern US. So I'm showing a plot depth on the vertical axis, and then this factor of safety ratio on the horizontal axis, and I'm showing it for 3 different magnitude events, magnitude 5.5, 6.5, and 7.5. And then also for 3 different peak ground accelerations, 0.15 G, 0.25 G, and 0.35 G. If we see this, it's not so, for at least the western US and central eastern US, there's not a large dependency on the peak ground acceleration. But we do see that this ratio is varying. At the shallow surfaces or shallow depths, the ratio is less than 1. At deeper depths, it gets greater than 1. Where this ratio is less than 1, this means that it's unconservative to use the Western US model. Where it's greater than 1, it's conservative. And even for all 3 magnitudes, you're not seeing a huge variation. So if you ended up using, say, the Bollinger and Idris 2014 triggering procedure in the central eastern US, yes, you may be unconservative or conservative at certain depths, but it's not going to be a big difference. We repeated this effort now for interface subduction zone events. And so I'm showing similar plots to what I did on the previous slide, only now for interface subduction zones. And my 3 magnitudes I looked at are 6.5, 7.5, and 8.5. Now you see that it's almost universally unconservative to use Western US relationship to predict liquefaction in these events. And also you see a strong dependency on peak ground acceleration, where for the lower peak ground acceleration, it's actually more unconservative to use the reference conditions as opposed to using region specific. Again, we repeated this effort now for induced seismicity. So we're now in Oklahoma, Texas, and Kansas. So we're in stable continental region. We see now the similar plots, only the magnitude range I'm looking at is magnitude 4, 5.25, and I can't see the third one because there's 6.5 is the third one. You're seeing actually that your predictions can be considerably conservative for these lower magnitude events at the depths that are predominant for liquefaction. As you get into the higher events, the range of being conservative and unconservative is lessened, particularly for these low events. You may be drastically over predicting the liquefaction response of the profiles. And my slides are not advancing. There we go. We did it again for the Netherlands. This is also induced seismicity for the Groningen region, but very different induced seismicity mechanism than what we have due to deep wastewater disposal in the Midwest in the US. This is from natural gas extraction. Profiles are also drastically different. So here you're seeing that it's not universally unconservative to use the Western US model, but for most cases, it's going to be. All right, so back to the simplified curve. Again, I show the factor of safety is going to be the CRR divided by the CSR, where both of these are normalized for our reference conditions. The question is then if we're interested in the damage potential for liquefaction, what is the impact of the thickness and the depth of the liquefied layer on the damage potential? So not just getting a factor of safety and then determining whether the site needs to be remediated based solely on this factor of safety, but now trying to predict what actually the damage potential will be. And the liquefaction potential index was developed by Iwasaki et al. In 1978. And I'm going to categorize this as a manifestation severity index model. So it's just one that I'm going to discuss. And what Iwasaki proposed is you perform your in situ test, you use the simplified triggering curve to compute your factor of safety. Then what you do is you take a weighted average of the factor of safety and you integrate it over the depth, maximum depth 20 meters, and then you come up with an index value, which is, in this case, will be your LPI value, and then you correlate that to what your damage would be. And mathematically, that is shown here. You have the LPI you're integrating over your depth of 0 to 20 meters. You have your weighting, depth weighting factor, and then you also have your weighting factor based on the factor of safety. The limits for this is an LPI would be the lowest value of 0, and the maximum value you could get is an LPI of 100. And based on some case histories from Japan, Iwasaki et al. Ended up finding out that if LPI was less than 5, severe liquefaction manifestations are not expected. And if LPI is greater than 15, severe manifestations are expected. The question is although what we do now is take into account both the factor of safety, the thickness, and the depth of these layers, there's other influencing factors on the damage potential, and specifically the influence of the non-liquefied crust, and then also the dilative tendencies of the soil at moderate to larger strains. And the basis for pointing out these two issues is work by Ishihara and his collaborators. In the left plot, what we're showing is the vertical axis is the thickness of the liquefied layer, which Ishihara designated as H2. And on the horizontal axis is the thickness of the non-liquefied capping layer, which he designated as H1. And then based on some limited data, and so a lot of judgment, Ishihara ended up drawing these three curves. And these curves correspond to different accelerations. They use the Galileo units for acceleration, but if you divide by 1,000, you're going to get it essentially into G's that we typically use in geotechnical earthquake engineering in the US. But if we focus on one of the curves, when your point falls on the left side, Ishihara is saying that you're going to end up having manifestations of liquefaction of the surface, which means that it could potentially cause damage. If your point ends up falling on the right side of the curve, he's saying that you'd have really no damage potential for that liquefaction. And again, he's doing this for 3 different peak ground accelerations. So this is showing or highlighting the influence of this capping layer on damage potential. And then on the right curve by Ishihara and Yoshimine, you're seeing on the vertical axis the factor of safety against liquefaction. On the horizontal axis, the post-liquefaction volumetric strain. And then you're seeing the solid lines, you're seeing contours for relative density. And the contour that falls to the leftmost is a 90% relative density, and the contour that falls to the rightmost is for a 30% relative density. So if you come in, say, for a given factor of safety of 0.6, you can see that if you have a dense soil, your volumetric strain is going to be much less than if you have a loose soil. And the amount of volumetric strain is kind of being used as an index for what the damage potential is. So now what we can do is try to merge those trends that we see that Ishihara came up with separate studies and incorporate those into manifestation severity models. And the first one I'll discuss is the Ishihara LPI. And this takes into account all the things that the LPI manifestation model did, but then it also takes into account the thickness of the non-liquefied crust. Alternatively, there was proposed the liquefaction severity number, or LSN. This accounts for everything that LPI does, but in addition, it accounts for the dilative tendencies of the soil at larger strains. So each of these, the LPI-ish and the LSN, account for one of those aspects that I showed on the previous slides. The LSI-ish for the non-liquefied crust, the LSN for the dilative tendencies of the soil at larger strains. So we incorporated all of these now into the Ishihara LSN, or LSN-ish. This takes into account everything that all 3 of these manifestation models account for. So it accounts for the thickness, depth, and factor safety of the liquefied layers, the thickness of the non-liquefied crust, and the dilative tendencies of the soil at larger strains. So now to assess how accurate these procedures are, or how good these manifestation models are, we took case histories from 3 of the Canterbury earthquakes: the 7.1 2010 Darfield earthquake, the magnitude 6.2 2011 Christchurch earthquake, the magnitude 5.7 2016 Valentine's Day earthquake. And this the aerial view on the left shows plots of these. These are generally fall in eastern Christchurch, and these are predominantly going to be sandy and silty layers. We're not going to have any of these interbedded non-liquefied layers in these profiles. Most of those, which is also of interest and have been studied, fall in the western Christchurch. And so in total, what we had was just over 7,000 case histories. We also excluded any case histories where lateral spreading was a predominant manifestation. So now what we did was we used those 4 different manifestation indices models in this database and assessed how well they predicted severity of liquefaction. And what we ended up finding out is that the 2 MSI models that account for the dilative tendencies of the soil ended up performing worse than the two models that didn't. So the original LPI model and the LPI-ish model performed better than the LSN and the LSN-ish model. And it isn't that the LSN and the LSN-ish performed badly, it's just that the LPI and the LPI-ish performed better. And the question becomes, why is that the case? Because we know that the dilative tendency of the soil directly influences the damage potential. And so now it's a matter of looking back and determining why we see the trends that we see. And what we end up figuring out is that we're double counting the influence of this dilative tendency at larger strains on the severity of surface manifestations. And the reason for this relates back to how we developed our triggering curve. So this is the figure that I showed earlier in the background section of the presentation. And I'm showing the case histories that are listed as liquefaction in green and then the no liquefaction in red. And instead of this actually meaning liquefaction and no liquefaction, what it actually means is that we predominantly had surficial evidence of liquefaction or no surficial evidence of liquefaction. So the no liquefaction point may mean that it actually didn't liquefy, or it may mean that it liquefied at depth, but it just didn't manifest at the ground surface. So taking a curve that's now being influenced by this dilative tendency and then throwing on an MSI model and using it in conjunction with it that also takes in the dilative tendencies now double counts that dilative tendency behavior. So the motivation now is to try to separate triggering from manifestations to properly ensure that we can refine each component of this model for a better prediction of the damage potential from liquefaction. So we went back to the same 7,000 some case histories, all from the Canterbury region of New Zealand. And we're trying now to separate the manifestation from triggering. And so we're defining this as the true triggering curve, not necessarily that it's 100% correct, but it's trying to remove the influence of the manifestation. So all the sites that we looked at were characterized by CPT. Now we need a triggering model, but again, what we want to do is use a true triggering model that's absent of any manifestation factors. And so now we're just going to assume a shape for this triggering curve. Then we're going to compute the factor of safety. We're going to apply the LSN framework because that accounts for the majority of the predominant manifestation factors that we think influence manifestation. And we're going to do this for all those 7,000 cases, and we're going to compare our predicted to observed surface manifestations. Then we're going to go back and we're going to revise the position of the curve. And we're going to repeat this process multiple times until we end up getting a triggering curve that gives us our best predictions when we work all the way through the triggering and manifestation that gives us the best comparison between the predicted and observed severity of surface manifestations. So we did this, and this was our triggering curve. Now, the data, even though we had 7,000 some case histories to drive this curve, realize and then compare that to the 13 that originally was used by Whitman and the 35 originally used by Seed and Idris. So we have 7,000. It's only from one region of the world and only from 3 earthquakes that impacted that one region. As a result, that data isn't able to fully constrain this true triggering curve. And so we had to use some assumptions on the shape of it, but we ended up thinking that it's going to be a straight line, and we performed it probabilistically. So I'm showing the median probability of liquefaction of 85 and 15%. Now, the benefit of doing this, and I think there's multiple benefits, is we remove the subjectivity of figuring out what our critical layer is. And for those that have developed the triggering curves before, when you analyze the case histories, you have to go through and figure out what you think is the critical layer. That includes the thickness of the layer and then representative properties for that. Because we're integrating through the manifestation model over the entire depth, or at least we're going down to 20 meters, there is no single critical layer. But we're considering within a total stress framework, all the layers are going to potentially have influence on the surface manifestations. And so it avoids some of the subjectivity in selecting the critical layers. So then we compared that to the high quality direct cyclic simple shear test. This was largely done by Kristen. Now I'm showing 4 points. That doesn't mean that we just had 4 points. Each one of those points is going to be derived from a curve developed from probably at least 10 or so tests, where we're plotting cyclic stress ratio versus number of cycles to liquefy, and we're pulling off the point on that curve that corresponds to the magnitude 7.5 event, which we're saying is 14 cycles. And so each one of these points is representing at least 10 tests. And when I say they're high quality, Kristen went through and developed quality control criteria for direct simple shear tests. And we ended up excluding, I would say, between 50 and 75% of the tests in our database based on that quality criteria. But if you end up comparing this curve, you can end up seeing that there's a fair close comparison between the 15% versus these tests. 15% is often used as a deterministic curve, and it's often used to bound majority of the field cases or the most susceptible soils for a given penetration resistance. As a result, there's no aging effects, and so the fact that it compares well to this 15% curve is encouraging. If we now compare it to the Bollinger and Idris 2014 curve, you can see at lower penetration resistances, there's not a big difference. It's not until we get into the denser soils that we're seeing the difference. But that's exactly what we expected, because we would expect at the denser soils, you would have that dilative tendency that could potentially prevent manifestations from occurring. So if we compare the two deterministic or probabilistic to probability of liquefaction at 15%, the difference between these of going from a linear line up to a curved line is because these dilative tendencies inhibit surface manifestations. And then to put it into a full probabilistic, or putting it in a performance-based design, we're proposing a probability of surface manifestations giving a certain LSN value versus LSN value. So now this allows you to go through, you would be using your deterministic curve, computing the factor of safety, running it through the LSN framework, computing your LSN, and this would then give you probability of surface manifestations for that LSN. So how we would use this in a forward analysis: for your project site, you would perform your in situ test. In this case, I'm showing CPT. You would then use your true triggering curve to compute your factor of safety against liquefaction. You would then run this through the LSN framework to compute an LSN. And in implementing this, you would be using a region-specific value for your CSR. And then also potentially you could modify this depth weighting factor to account for things like interbedded layers. And so this would be developed from future work, not anything that we have now, but it is some work that is ongoing. And then if you wanted to go through and do the full probabilistic, then you would go in and use this curve for your LSN value, and this would give you your probability of surface manifestations given that LSN value. So in summary, the simplified triggering model are for a set of reference conditions. Regional relationships are needed to account for the differences in the soil profiles and ground motion characteristics relative to the reference conditions. The traditionally derived triggering curves inherently include effects of both triggering and manifestations. And then in conjunction with the new manifestation model, an iterative approach was used for proposing a true triggering curve. And by true, what I'm saying is it's absent of factors influencing surface manifestations, or at least to a first attempt at doing that. And again, I put this slide, I think, is my second slide or so, but I would also, again, like to put it as the last slide, just to acknowledge the many people that contributed to this work that I'm presenting, and then also the funding agencies that supported it. And with that, I would like to open it up to questions.
Thank you so much for that wonderful presentation. I'll just remind all the attendees, if you have a question, you're welcome to put a question in the chat or in the Q&A panel of your WebEx interface. You're also welcome to raise your hand if you'd like to ask your question live, and I will try to keep an eye on who's got their hand raised and who has a question. So with that, I think I see a question in the chat. Russell, would you like me to read it out?
Yeah, please. I'm not very proficient with the WebEx.
No problem. It's a question from Shade Dashti asking about how the probability models came about for the true liquefaction triggering curves using the empirical database. Did this come from total or effective stress analyses of the profiles from the case history database, or the actual empirical data? Could you clarify?
Yeah, so everything was a total stress analysis using case histories. And so the probabilities that I'm showing there are similar to the probabilities that were developed for the other existing triggering curves by analyzing the field case histories. And it was using a total stress approach.
There was a second question she had as a follow-on. In the case of analyses, what is our definition of triggering in this context?
So it's actually, the triggering curve is a curve that results in the factor of safety when you integrate using the LSN that's going to result in a manifestation or absent of a manifestation. And so it's hard to say how triggering is specifically defined within this framework. It's simply going to be the curve that when you put it in the LSN framework, it either results in triggering or manifestations or not at the surface.
So I see two other hands up. So I think I saw Scott's hand up first. So Scott, I'm going to invite you to unmute so you can ask your question.
Can you hear me?
Yes.
Yep.
All right, great job, Russell. Thanks a lot for coming to the presentation. I had a question just about, the difference between the true triggering curve and the original triggering curves at high relative density, because there's now a significant difference where your method, correctly points out that these relative density higher than 80% or something can liquefy. We know that from lab tests, but a lot of people don't worry about those because they plot beneath the red lines here. So, have you had cases where engineers may be working on pile foundations that are founded in a dense layer, and now they have to worry about liquefaction at the tips of those piles, whereas before they might not have had to worry about it, even though the layer might not manifest all the way to the surface, right? Doing an LSN or something, it still may liquefy and lose capacity at the tip of a pile or something like that.
That's right. So no, we haven't had that case because we haven't published this yet. So I'm working on the draft manuscript now. We published different pieces of what I presented, but we haven't tried to publish the true triggering curve. But you're exactly right. And that goes back to this right here. So I had I had explicitly pointed out, if you have these interbedded layers, non-liquefied layers, that you might want a different depth weighting factor that accounts for those. But this framework, what I'm showing here, corresponds to just surface manifestations. If you have deep foundation systems, this also would be a different weighting factor. So everything up to this weighting factor would be different. And you're exactly right. We might be unconservatively evaluating piles because this material may liquefy at depth that might not manifest in a free field at the ground surface, but might end up causing damage to the pile foundation system.
Great. Yeah, I didn't know if anybody had brought this up in a heated argument with you at Geo Congress. Maybe they're waiting for the paper to come out.
No, so I did receive some mixed results. Ross was very encouraging, which was nice. But he also prepared me when I submit the paper for review that it's probably going to be a tough one to get through the review process because of issues like this.
Any paper worth publishing has a good chance of being declined. Thanks a lot. I enjoyed this very much.
Thank you.
Okay, I see John Stewart has his hand up, so go for it whenever you're ready.
Yeah, I also really enjoyed the seminar. What you've talked about in separating liquefaction triggering from manifestation is something that is really being taken up very seriously in this project, the NGL project. So I think we're very much on the same wavelength, and I think that different people will take different approaches in making that separation. So it's really wonderful to see you putting all this together and actually pushing a model out. My question for you is about the other part of your presentation on the regionalization. And it seems to me, in listening to what you were saying there, that regionalization is, in this context, factors of safety and so on, is really an outcome of the fact that ground motions and soil profiles are regional, such that if you were to, and frequency content, but frequency content is part of ground motions. So if you had a liquefaction model that was directly using the appropriate number of ground motion intensity measures, and if you had an R sub D type model that was appropriately using attributes of the VS profile, then you would just put those in for your site, whatever region it's in, and then things wouldn't be regional anymore.
That's
Do you
right.
agree with that?
Yeah, you would be mapping it back to your reference conditions. Exactly right.
Okay.
So your triggering curve is your triggering curve, regardless of whether you do true triggering curve or the existing triggering curves. You're taking your site and you're mapping it back into the reference space.
Right. Okay. Yeah, I just wanted to make sure that I understood your argument. I think the one exception to that would be that, one could imagine that perhaps the mineralogy or the geologic conditions at deposition might be systematically different in one region versus in another. To use like an extreme case, suppose we took Hawaii. And, they have a very different type of mineralogy there. So then you're talking about the material behavior itself being different, and which is, a separate thing from the ground motion characteristics.
It is, and one of the things that I removed from the presentation that I gave in Charlotte, although even in Charlotte it wasn't emphasized heavily, is the K sigma factor. And so we're proposing a new K gamma factor, which actually does incorporate a lot of the intrinsic soil properties and then also the stress states. And so I actually proposed presenting on that, but Kristen preferred this, which is absolutely fine. But there is that factor that we're replacing K sigma with K gamma that does take into account intrinsic soil properties, at least to a certain extent, that may help with some of that. I don't know if it would necessarily help with volcanic or calcareous materials, but it certainly would help with aged materials.
Yeah, but I think the framework whereby you have a liquefaction triggering curve, and then you do the manifestation separately, the triggering curve could be mineralogically varying.
Yeah.
It would take us a while to work all that out as a profession, but one could imagine a future where we have different curves for different depositional environments, different minerals.
So just to elaborate on the K gamma factor, if you look at the original work by Dobry, but also Martin, Finn and Seed and others at British Columbia, they end up showing if you use strain independent of the soil mineralogy and aging of the soil and even stress conditions, you end up seeing that the correlation between number of equivalent cycles of strain and excess pore water pressure is fairly constant. So what the K gamma factor does, and the reason why it's gamma is because it relates to the shear strain, what it does is equate shear strains for the different minerals. So as opposed to doing it as a capacity term like you're talking about and having a separate triggering curve for each mineral, what it's doing is it's mapping it back in terms of the demand in terms of strain. And so you would be now having a reference strain condition and you would be mapping it back to that.
Yeah. Yeah. Yeah, so maybe the strain response of the soil is less sensitive to mineralogy. It's more manifest on the stress side.
That's what we're proposing, or that's
Yeah.
what we're hypothesizing.
No, I can see that. Great, thank you.
All right, I see we have another hand up. Today has a question. I'll allow her to unmute. Go for it.
Hey, Russell, thank you for your clarifications and for the seminar, truly valuable work, and thank you for sharing it with us. Another question that came up, just for my own clarification, if the definition of triggering in the true triggering curves is related to manifestation, as you explained, and if I understood correctly, how can we distinguish between the two? Wouldn't it be more reasonable to relate triggering to fundamental soil response like pore pressure and shear strain from effective stress analyses of the profiles, and then compare them with manifestation to truly keep them separate?
I don't disagree with you. And there, as I had mentioned, when we did this iterative approach to developing the true triggering curve, we ended up having to go back to laboratory tests and kind of help it guide us what the shape that we picked on this. And so this is where your judgment is coming in, and we were using laboratory tests in helping limit this functional form. So you can imagine when you're doing this iterative procedure of assuming a shape and revising it, you have an infinite number of not only functional forms, but then also the regression coefficients for those different functional forms. And even though we have over 7,000 cases, it's still not enough to fully constrain this for just any type of random curve. So what you're proposing is that you help constrain that, or your judgment can be input into that triggering such that you're basing it on laboratory tests where you know what's triggering because you're defining it in a certain way in the laboratory. And we actually did do that. It isn't necessarily that everybody's going to agree with the judgment that we use, but we are guided by that in selecting the functional form for this triggering curve. So yes, I agree with you. And I think where that would be input is essentially here. And if you get that right and your LSN model is correct, which may not be, your LSN-ish model is fully correct, which again could be using some potential revisions, then it should actually result in something that what you're saying is truly representing triggering.
Okay, great. Thank you. I'm looking for any other questions. I don't see, oh, I see Steve, your hand is raised. Go for it.
Hi, Russell. Thanks also for your presentation. It's really very interesting. I'm wondering if you have applied this to any other data sets besides Christchurch, and whether you've seen variations in what you would get if you did that.
We did. So in the paper that I talked about that we're currently working on, and it's 95% done or so. So when I say I'm working on it, it's not that I have all the ideas in my head and just haven't written it. It's 95+% written. So what we did was a validation exercise where we took 50 worldwide case histories and we evaluated those, and we used the LSN model, but the way we computed the factor safety was one using this triggering curve, or what I'm referring to as the true triggering curve, and then the Bollinger and Idris 2014 triggering curve. And then we ended up comparing how successful we were in predicting manifestations or no manifestations. And we got about the same predictions with the true triggering curve versus the Bollinger and Idris. And that may seem like, well, you're not doing any better, but realize this true triggering curve is only developed from 3 earthquakes in one small region of the world. So I don't expect this to be the final curve. I'm presenting this more as a framework. And also the Bollinger and Idris procedure was actually based on those 50 case histories, among others, 200 plus others, where this one wasn't. And so yeah, we did do the validation only with 50, and we ended up showing up that we do fairly well given the limitations that this was based on only 3 earthquakes from one small region of the world. And there is some bias in the Bollinger and Idris in that they were actually, their triggering curve was derived on those 50 case histories, among others.
Right. Okay, thanks.
We have a few minutes left. If anyone else has any questions, feel free to raise your hand or enter a question in the chat. I don't see any at the moment. Oh, I see one now. Just came in. This is from Patrick. If you'd like to unmute yourself and ask your question, you're welcome to, but I'll read it out. It says, is QC1 NCS as you have based it, or as you have it, based on the original Bollinger and Idris 2014 formulation?
Yes. Yeah, so the normalization that I used for all these case histories was based on the Bollinger and Idris 2014. These were for only really clean sands and silty sand profiles. I didn't get into any interbedded layers or thin layer corrections, and we specifically selected the case histories to avoid that. That would add another level of uncertainty in our data. If no one has a question, I'll tell you what Ross posed to me. He said that he worked on a project where he convinced the people that they needed to perform soil improvement, and they were using penetration resistance now to evaluate their quality assurance to ensure that they improve the soil. And he's saying it's going to be tough now to tell them after all the time and money that they spent that they're still going to liquefy. And what you're doing is transferring whether you liquefy or don't liquefy to actually what's going to be cause damage. And so in reality, what you're doing is regardless of whether you liquefy, and this is showing for Ishihara that he's got a 90% relative density, and he's showing factors of safety against liquefaction down to 0.4. So he's saying 90% relative density soil will liquefy. But because you get very little volumetric strain, it doesn't matter. It's a matter of now going to performance-based design type criteria where, yes, it may liquefy even though it's 90% relative density. The effort and money that you put in to densify the soil is to reduce the consequences, not whether it will trigger or not. And so it really takes the heart of this curve where you're showing you can actually liquefy dense soils. It's just you're going to have minimal consequences if they do liquefy. That may not sit well with a lot of regulators or practitioners just based on what we've done in the past, but I think it's technically and mechanically sound.
Thank you very much for adding that in there. I don't see any other questions or follow-up here. Oh, I see. Sorry, the one last one from today says, I'm a bit worried about judging damage based on volumetric strain without considering SSI. Any comments on that?
Volumetric strain isn't being used as a value for volumetric strain. It's being used as an index for its dilative tendencies. And so even though this is related to volumetric strain, the way that it's incorporated in these MSI models is just an index of your dilative tendencies of your soil and then therefore your damage potential of your soil. So now throwing on SSI analyses on top of this certainly would be valuable, but you'd have to take this as a first step unless you're going to be jumping directly into an effective stress type analysis with piles and a building on it. And then the problem with that is, although you can predict a response, it's validating the response. This is kind of incrementally moving towards something like that to allow you to validate that.
Okay. And Steve has, I think, the final question.
Yeah, Russell, in terms of this manifestation severity or maybe damage severity, do you think it would make more sense to be looking at shear strains instead of volumetric strains?
You could.
They often drive the deformations that we're concerned about.
I think they're going to be inherently related. And if you look at the curve, and I'm doing this off the cuff, but you can see that there actually is a maximum shear strain associated with these contours. So you're going from the solid contours now down to the dotted, and I would have to look at trends, but intuitively, I think they're related, that if you were predicting a large volumetric strain, then you would be predicting a large shear strain or allowing for a large shear strain. But I would have to go through and specifically look at the trends that are being shown here for that.
Yeah, I agree they're correlated. I think the idea of a maximum volumetric strain makes a lot more sense to me than a maximum shear strain.
Yeah, again, the volumetric strain is just being used as an index for the dilative tendencies. And if we use shear strain, we would do the same thing. I'm not trying to predict the maximum shear strain. I'm just using as an index for the dilative tendencies and relating that to the damage potential.
Yeah, okay.
I think with that, we have reached the end of our time. Thank you so much, Russell, again for presenting. I will make one last plug too to everyone who's attending the NCE conference at the end of the month. Come to our NGL special session on Tuesday morning during the conference.